Hello and welcome to this complete topic revision video on Year 1 Equilibria. Many chemical reactions are reversible. This means they take place in both the forward and reverse directions. This symbol indicates that the reaction is in equilibrium. But what does equilibrium actually mean? Merriam-Webster defines this as a state of balance between opposing forces or actions. Reactions in equilibrium, otherwise known as equilibrium systems, are always moving. We call this dynamic. A typical exam question might ask us to identify the two features of dynamic equilibria. These are the rate of the forward reaction is equal to the rate of the reverse reaction, and the concentrations of reactants and products do not change. For a system to remain in equilibrium, it must be closed. For example, a sealed reaction vessel. In this way, the reaction is isolated from its surroundings, so it cannot be affected by external factors such as temperature, pressure, or change in concentration. In the late 1800s, Henry Louis Le Chatelier came up with his principle, which states, when a system in equilibrium is subjected to an external change, the system readjusts itself to minimize the effects of that change. If temperature, pressure, or concentration are changed, the position of equilibrium may move. Let's look at the effect of change in concentration first. Imagine we increase the concentration of B. This will move the equilibrium to the right, to the product side. It does this to use up the excess B, reducing its concentration and thereby minimizing the effect of the change. What if we were to reduce concentration? If we reduce the concentration of B, the equilibrium will move left towards the reactants. This will result in more B being formed, increasing its concentration again and minimizing the effect of the change. Next, let's look at the effect of change in pressure. This only applies to reactions with gases, since they can be compressed, whereas liquids, solutions and solids cannot. Gas pressure is proportional to the number of gas moles present. This equation shows that 2 moles of sulfur dioxide react with 1 mole of oxygen to form 2 moles of sulfur trioxide. There are 3 gas moles altogether on the reactant side and 2 gas moles on the product side. The pressure is highest on the side with the most gas moles. If we were to increase the pressure, the equilibrium would move to the side with the fewest gas moles. This would reduce the pressure, thereby minimizing the effect of the change. In this example, the reaction would move towards the right-hand side, the products. Whereas if we decrease the pressure, the equilibrium moves to the side with the most gas moles. In this example, it will move to the left, the reactant side. Now let's look at the effect of temperature. For this, we need to look for an enthalpy change value. The enthalpy change is always to do with the forward reaction, and the negative sign tells us that it's exothermic. So if the reaction moves in the forward direction, to the right, energy is released, and that energy release causes the temperature of that reaction or system to increase. If the forward reaction is exothermic with an enthalpy change of -197, that means the reverse reaction must be endothermic, with an enthalpy change of +197. In the endothermic direction, energy is absorbed from the surroundings into the system, causing the temperature of the system to decrease. Imagine we increase the temperature of this reaction. The position of equilibrium will move in the endothermic direction to minimize the effect of that change. In this example, it will move left. If we decrease the temperature, the equilibrium will move in the exothermic direction, in this example, to the right. What about the effect of a catalyst? A catalyst does not change the position of equilibrium, since it speeds up both the forward and reverse reactions by the same amount. This means that the same position of equilibrium is reached faster. We can quantify the position of equilibrium by calculating the equilibrium constant Kc. Kc is a ratio of products to reactants at equilibrium, raised to the power of their number of moles. If we look at this equation for the Haber process, we could write the Kc expression for this reaction like this. So Kc is equal to the concentrations of the products raised to the power of their number of moles over the concentrations of reactants raised to their power of the number of moles. And if there's more than one, we times them together, but we don't actually need to show the multiplication sign. And remember, square brackets mean concentration of the thing that's inside the bracket. The Kc value tells us where the position of equilibrium lies. In other words, it tells us about the extent of the reaction. If we calculate Kc, and we'll see how to do that soon, and our value is greater than 1, that means that the equilibrium is towards the right-hand side, towards the products. If we calculate our Kc value and it's any number that's less than 1, the equilibrium is towards the left-hand side, towards the reactants. So in this case, we'll have more reactants than products. If we calculate Kc and it's exactly 1, that means the position of equilibrium is in the middle between reactants and products. Let's have a look at an exam question then. So I've got these from 2 different OCR papers, and I've picked things on what we've looked at in this video today. The first one, a multiple choice, what is the correct expression for Kc? So if you want to have a go at this, then pause the video now. We know that Kc is the concentration of products raised to the power of the number of moles over the concentration of reactants raised to the power of their moles and multiplied together. So the only one where that is true is this one. So the correct answer is B. This one here, it wants the expression for Kc, so let's do that first. And it's to do with this same equation. So we've already identified the Kc expression as being this. And we need square brackets because that means something. That means concentration of the thing that's inside. Now in year 1 chemistry, we'll be given the equilibrium concentrations, which we can just plug in to this expression. So we've got SO3 here. And just remember to raise it to its power. And now we can use curved brackets because these are numbers now. So now we're using the numbers, they don't have to be square brackets anymore. Pop that in our calculator and work out an answer. So we should end up with a really big number. So I'm going to jot that here, 79365.07. So I'll leave it to the nearest whole number. But what does the question say? Appropriate number of significant figures and in standard form. So if we look here, we've got 2 significant figures. So I want this to 2 significant figures and in standard form. So it's going to be 7.9 times 10 to the positive 1, 2, 3, 4. So that big Kc value, or just the fact that it's greater than 1, tells us that the equilibrium is very much towards the right-hand side. So this reaction favours the products. Then this bottom one here, it says in the industrial production of SO3, so it's talking about the same reaction again up here. An excess of oxygen is used instead of the 2-to-1 proportion of SO2 to O2, which would match the stoichiometry. So instead of this 2-to-1, they use an excess of oxygen. Suggest why an excess of oxygen is used in terms of equilibrium. So what the question's actually asking us is what will happen to the position of equilibrium if we add more oxygen than is actually needed for that reaction? Well, we know that it will shift to the right. We can just say because it will move the position of equilibrium to the right. Let's finish with one more exam question then. So this question is about applying Le Chatelier's principle, and the question says, hydrogen gas can be produced as shown. Which conditions produce the greatest equilibrium yield of hydrogen? Now, hydrogen is one of the products, so the question's asking us, how can we shift the equilibrium to the right? If we look at the enthalpy change value, we can see it's positive. That's telling us that the reaction is endothermic in the forward direction. In order to shift it in the endothermic direction, in the energy absorbing direction, we need to increase the temperature. So that narrows it down to either C or D as the correct answers. The next thing is that this reaction, everything's in the gas phase, so we can count our gas moles. We've got 2 gas moles on the left, 4 gas moles on the right. If we want to shift it in the forward direction to the right hand side, that's the side with the most gas moles, so we need a low pressure to do that. I hope you found that helpful. If you did, please like and subscribe for more. See you again soon. Bye.